I used to run up that hill. Not anymore. If it wasn't for Gianluigi who picked me up, I think would still be trying to get up the hill. So let me just say that it's a great pleasure to be here and see many old friends of mine, not least the chairman here, who was my postdoc a few years ago in the 1980s. And I'm going to tell you about how to rule out cold dark matter, which is what I've been trying to do for a long time. So when in the 1980s, the idea that the dark matter might be an elementary particle was proposed, it was very soon realized that independently of the mass of this particle, they could all candidates, non-baryonic candidates, could be classified into, how do I point in here, Fabrizio? I cannot point in here. All right, they could be classified into 3 families, hot, warm, and cold dark matter, whose properties just depend or reflect the thermal velocities of these particles during the Big Bang. So hot dark matter, the best example would be a neutrino with a mass of a few tens of electron volts. Cold dark matter, the mass could be anything actually that's out of date, could be from 10 to the minus 22 eV all the way to a TeV or more. In those days, in the 1980s, there were no candidates for warm dark matter, but now there is a very attractive candidate, the sterile neutrino, that Alexei is going to tell us a lot more later. Now, so the reason for this simplification can be seen here. The plotted here is the power spectrum of density perturbations as a function of scale. So large scales are on the left, small scales on the right. There's no way to get rid of this, Fabrizio, is there? Of the fringe at the bottom, is there? You mean I can point?
You should not point with that.
But it's better than not pointing. Thank you.
Get rid of
All right. Okay. So
be able to point.
yeah, no.
Okay.
All right. So what the power law you see there that says n equals 1, that's what inflation predicts. So this is the power spectrum of density perturbation. Inflation predicts a power law with a slope just slightly flatter than 1. And then depending on the thermal properties of these particles, the power spectrum can get cut off. So if the particles are hot, then there is, that's due to free streaming, there's a cutoff on the scale of galaxy clusters. If the dark matter is cold, there is actually a cutoff, but it's way here at the mass of the Earth for a standard neutrino, for a standard WIMP particle with about 100 GeV. And then in between, if depending on the mass of the particle, the cutoff scales like roughly like 1 over the mass. So for example, if the mass is a few keV, then the cutoff would occur on the scale of dwarf galaxies. So that was clear already in the 1980s, very soon after these ideas were put forward. And what was very exciting is that these possibilities can be tested with astrophysics. So how do we test this? It's a beautiful problem because it's all very completely specified, at least insofar as the evolution of dark matter is concerned. And so all you need to do is to go from those power spectra to the universe today. The best way to do this is using computer simulations, whereby you essentially start with some assumption about the contents of the universe, and that completely specifies the initial conditions. That's a beautiful computational physics problem because the initial conditions are known, and also, of course, the interactions between the components of the simulation are known. If you're interested in the dark matter, all you need to do is solve the collisionless Boltzmann equation, the Poisson equation, and the Friedmann equations. If you're interested in more complicated parts of the universe, like what we can see, the baryons, then the problem gets more complex, but it's still all well understood, essentially 19th and 20th century physics. So you program a computer to solve these equations. You know the starting point. If you make some assumption about whether the universe is made of cold dark matter or warm dark matter or whatever, and then you program these equations and you see what comes out at the other end. So that's the program. Now, the first thing to try in the 1980s was a neutrino, because in those days, it was worse than today. There was an iron curtain between the USSR and the West, but news had filtered through the iron curtain that Novikov, Lyubimov, Novikov, and colleagues had actually measured the mass of a neutrino and they measured it to be 30 electron volts, which is just perfect. We know how many neutrinos the universe has, 100 per cubic centimeter, roughly, you know the mass. Then this was enough to provide the critical density. So it's very exciting, but the excitement lasted very briefly because it soon became clear that a universe like that, in which the dark matter is made of massive neutrinos, and it has a closure density, then it didn't look anything like the universe as we knew it then. That was the biggest redshift survey at the time, 2,140 particles. And it was clear that a universe of massive neutrinos didn't really look anything like a real universe. So that was the first concrete result from this program. The neutrinos couldn't be the dark matter. And moreover, it follows from here that the Lubimov experiment had to be wrong, and that the neutrino, if it has a mass, it had to be a lot less than an EV, which we now know to be true. So it shows you the power of cosmology to tell you interesting things about particle physics. Now, we then, we acquired Joseph Staffew, and we then ran the first, what is now known as lambda CDM simulation. The hope was that we could rule it out as quickly as we ruled out the massive neutrinos. That was the hope then. This is 1985, and I've been trying to finish that program and rule this out for the last 40 years, but I haven't succeeded yet. So, but you can see just by eye that a lambda CDM universe looks a lot more like what we see around us. Now, so the now I'm going to tell you that the properties, justify this in a minute, the properties of the dark matter distribution on all scales, from the Earth mass to galaxy clusters, is now a problem that has been solved. It was only solved recently, but it's completely solved. So if we were to live in a universe made of only dark matter, then we know exactly everything we need to know about the dark matter on all scales. It's a composite of simulations. It's thanks to the work of simulations of many groups around the world. These are the simulations I'm involved in from something called the Virgo Consortium. And I'm going to justify this statement in a little while. Now, the simultaneously, there's been enormous progress also on the observational surveys of the large-scale structure. So this is a picture of the Sloan survey. And we went from 2,000 galaxy surveys, redshifts, to Sloan that has about a couple of million. And now, in fact, there's another order of magnitude increase. There's this very exciting program called DESI. And DESI will already has about 10 million spectra. And in the next 2 years, it will collect another 30 million spectra. And here you see an amazing picture. Unfortunately, the screen is too small for the auditorium, but if you were able to come close, you would see this incredible cosmic web. The detail here is just enormous. It's just tremendous. It's very exciting to see what the universe around us looks like. And just for reference, that is what the CFA survey, that's what it corresponds to. And this is just an insert of the much bigger survey that. And this is just one of the surveys. It extends to redshift 0.5, and we will get a huge amount of science from this in due course. And the great thing is that one can measure properties of the galaxy pattern to 1% accuracy. I must say, I never believed that this was possible. I used to work on large-scale structure, and when people started talking about precision cosmology and 1%, I said, forget it. I started working on something else. But now I'm a convert, and I believe that it is possible to measure statistics to 1% accuracy. And so it's very exciting for a number of reasons, some of which I will come to later. So we can then compare the simulated world on the right to the real one on the left. And you compare this one to that one, this one to that one, that one to that one. And you can see that the correspondence is pretty spectacular. And of course, you can, but what really turned these sort of ideas into the standard model of cosmology was the measurement. First, the discovery of fluctuations in the microwave background radiation in the 1990s, but then finally this glorious plot that everybody here has seen, where you can, the green line here is lambda CDM. You cannot see, well, these are predictions from Jim Peebles in 1991. And Joseph Staffew and Dick Bond, and then in red are, of course, the measurements. And this is one of the most glorious plots ever. So if you don't get excited when you see this, then you shouldn't be a physicist. Physics doesn't get any better than this, in part because the predictions predate the data by decades. So these are predictions made in the 1980s, sorry, 1991, as I said, and then measurements in the last decade or so. So wonderful agreement. And so let me just summarize CDM. It's proposed in the 1980s, is now empirically supported by these observations when the universe was 1,000 times smaller than it is today, and also by the pattern of galaxy clustering 13.4 billion years later. Here is a quantitative statement of what you can see there. Here's, again, the power spectrum that I showed you earlier. And you see the CMB fluctuations in red, extrapolated to redshift 0 using linear theory, where you can compare them with the measurements of galaxy clustering. And the agreement is, as we say, really sensational. However, great as this is, it doesn't tell us anything about lambda. We have no idea what it is. And more worryingly, it doesn't tell us that the dark matter is called dark matter. Because, for example, if the dark matter was a warm particle, say a stellar neutrino, then the cutoff occurs on scales that are not probed by any of these observables. All the success of CDM transfers directly to warm dark matter. And of course, we'll be none the wiser, but of course, this makes an enormous difference to physics, whether the dark matter is a cold particle or a warm particle. So I'm going to tell you later how we can distinguish between them. Now, so here's just by eye, you can see here on the left is what the halo of the Milky Way should look like if we live in a universe made of cold dark matter, and on the right, the equivalent in a universe made of warm dark matter. Because the cutoff in the power spectrum, you see far fewer substructures in the warm dark matter universe. So now let me tell you now why I made that statement, that the properties of the dark matter distribution on all scales is a solved problem. So what do we know? We know everything. And I'm just going to tell you briefly, actually, about the first two of these. We know the halo mass function now of halos of all masses, from the mass of the Earth to the mass of the galaxy cluster. I'm going to show you that in a second. We also know what the internal structure is predicted for these halos. I don't have time to talk about the special distribution, but we know it also to 1% accuracy. So now how do you do that? So here's the power spectrum with the cutoff. And until recently, the best simulations we had would only sample one part of the power spectrum down to the scales of small dwarf halos, if you like, 10 to the 8, 10 to the 9. This is the state of the art until a few years ago. We're still many orders of magnitude away from the cutoff in scale, and then many, many more orders of magnitude in mass. So how do you get the halo mass function all the way to the mass of the Earth? Well, it's not easy, because if you just try to do it by brute force, doing a simulation where you resolve planets and you resolve galaxy clusters, well, it's impossible. You will need 10 to the 27 particles. That's impossible today, and will always be, well, I don't know if always, but will be impossible for a long time. Now, so what you have to do is come up with some trick or clever strategy, and that's what we did. I'm going to show you results from a paper in Nature by those people over there on the top. And so the strategy we adopted was this. We did a cosmological simulation. Then we found a region of low resolution, a void. VVV stands for voids within voids within voids. So we found the void, and then we did the simulation again, but putting 100 times more resolution in this region. Now that you can do because it's a low density region, so computationally it's much easier than if you had a big cluster there. So we do that. So here, the typical objects you see here are 10 to the 14 solar masses. Then when you do the resimulation, we're always resimulating the entire original volume, but focusing in these low density regions. So here's what you see at the next level of resolution. Now the typical objects you see here are galaxy clusters, and then you find a void, a low density region. You resimulate it again. Here, these objects are 10 to the 9 solar masses, and now they are about 10 to the 6. And you keep going. This is level 3. Level 4, the typical objects are 1,000 solar masses. Level 5, 10 solar masses. So these things are 10 solar masses. And then these ones are 1/10 of the solar mass, and we're not finished yet. And of course, the scale is shrinking, but every time we're simulating the whole big volume, just resimulating, increasing the resolution in these regions. This is now 10 to the minus 4. So these blobs you see here are 10 to the minus 4. And then finally, these are Earth mass. So in this way, we were able to simulate the whole hierarchy from the mass of the Earth to the mass of a galaxy cluster. The scale here is 25 parsecs. I never in my life thought I was going to do a simulation where the particle mass is 10 to the minus 9 solar masses, but that's what this is. And here's the answer. So years of work, we actually managed in this project to break not just Adrian Jenkins, who is very, very hard. I mean, he's immensely competent, but we managed to break Volker Springel, and not just once, several times. But Volker, of course, recovered and put all the pieces back. Extremely difficult, technically challenging, because you have this tiny little region that's moving at 600 kilometers per second in this 100 megaparsec volume, and having codes that can do that is not easy. And all that for this plot that looks totally boring. It's just a straight line with a cutoff, and even the lines are slightly wiggly. They're wiggly because there's lots of technical detail here. It's a convergence test, not in there. But what's remarkable about this plot is the number of orders of magnitude on the two axes. So this is 25 orders of magnitude in abundance, 25 orders of magnitude in mass. So this is it. This tells you about all the halos that exist in the universe. We know exactly how many there are, and then there's a cutoff, an exponential cutoff here at large masses. So now this is the most fundamental prediction of CDM. So it couldn't get more fundamental than this. Of course, in the absence of baryons, and I'll come back to how we can test this mass function in a little while. Now, so by contrast, in the case of warm dark matter, you can use it by eye here. There are far fewer substructures, and there the halo mass function is cut off at a mass. So there's a particularly interesting, Alexei will tell you why, a version of the warm dark matter model with a stellar neutrino of mass 7 keV. And in that case, there are no halos of mass less than a few times 10 to the 8. So completely different predictions. You think in principle we can tell them apart by looking at the universe. Now we know not only the number of halos, but we also know their structure. And this has been known for a long time that if you make plots of the density as a function of radius of halos of all masses, well, here they're just from dwarf galaxies to galaxy clusters, they're all fit by a very nice, very simple formula. And if instead of using physical units, you use dimensionless units, then all these curves collapse into one universal profile, which is the NFW profile that diverges as 1 over r towards the center and falls as 1 over r cubed in the other part. So now this was already pretty impressive. It's 4 orders of magnitude between 10 to the 11 and 10 to the 15. And sorry. Oh, right. And now, so the question is, so I should say the NFW profile is not perfect. It gives you a fit. You can see there the residuals with an accuracy of 20% or so. And then in 2008, we introduced this Einasto profile, which officially, anyway, so we realized if you want to have a little bit more accuracy, then of course you have to introduce another parameter, this alpha, which is a shape parameter. And Einasto had used the same formula to describe counts in the halo of the Milky Way. That's why in honor of Jana Einasto, we gave this the name the Einasto profile, and that gives you an accurate answer to a few percent. But of course, at the expense of another parameter and at the expense of the simplicity of the NFW profile. The NFW profile really is universal. If you give me the mass of a halo, I can tell you everything we need to know about the average halo of that mass with no free parameters. Right. So now what happens to the Earth mass? Well, here it is. Here's a plot of the structure of halos down to the mass of the Earth. Now, in fact, they're very well fit by NFWs, maybe surprisingly, maybe not. So well fit that I'm showing you there, not the density as a function of radius, but the derivative of the density. That's the slope of the profile. It's so good that you can get away with that. And as before, the NFW gives you an accurate result to 20% or so, and Einasto to a few percent. And the red here are the mass of the Earth. And whatever that color is, that's the mass of the coma cluster. So the NFW really is universal. It applies all the way to the mass of the Earth. This is the concentration mass relation, which is something that many people need to use for calculations. And that was a surprise. The concentration goes not unexpectedly up until we approach the cutoff, and then it actually goes down because there's an effect to do with the cutoff in the power spectrum. And all these are lines. When we only had simulations here, people would extrapolate, and everybody's wrong. Everyone except for one study by my former postdoc, Aaron Ludlow. Aaron Ludlow is the only one that came anywhere close, but all the other extrapolations are wrong, including our own. In fact, the worst one is our own, which is the blue line by Neto et al. And in 2007, this one, sometimes by factors of thousands. So everybody who needs a concentration mass relation, throw away everything you have and use this one. Now, so the now I'm going to make slight digression because I'm going to come back to how you rule out CDM. But this is so exciting. I just want to show you this. It'll just take me a couple of minutes. And that goes back to what I said before, that this is going to measure a clustering statistic to 1% accuracy. Now, so I just want to tell you for 2 minutes about neutrinos. It takes me back to the early days of my career. But these are not 30 electron volt neutrinos. These are a fraction of a electron volt neutrinos. So neutrinos are the one particle that we know is dark matter. That's the only dark matter particle we know, but it makes up only about 1% of the total amount of dark matter. Now, if we could see these neutrinos, they come from not recombination, they come from much earlier. There's a background here of neutrinos, also about 100 per cubic centimeter, that comes a few seconds after the Big Bang. So if we could detect this neutrino cosmic background, we would be able to see all the way back to the first few seconds of the Big Bang. So what would that background look like? And I should say there's an experiment called Ptolemy that is being designed as we speak to try and discover the cosmic neutrino background. So how does that work? Well, I'm going to show you some work from my former student. Whoops, sorry. Where did I go? From my student, who's now my postdoc, Willem Elbers. Here are the authors of this paper. It was just posted, I think, a few weeks ago. And so what we wanted to know is we wanted to make a prediction for what a neutrino background experiment would see if it points out into the sky here. Now, in fact, it would see, as I'll show you in a minute, the large-scale structure, the local large-scale structure. So the first thing we needed was a simulation of how the neutrinos behave locally. And so for that, we used a technique known as constrained realization simulations, where it's a CDM simulation, but the phases of the fluctuations are adjusted such that you get the observed large-scale structure. And so here are results of this, it's called the Sibelius program, led by my postdoc, Til Zavala. And you see here predictions, well, or the results of the simulation for shells of different radii. And you can see in the simulation, this is just simulation. There's no real data here, but here you see the Virgo cluster forms and the Fornax cluster, further away Centaurus, Coma, and so on. So this can be reproduced, but this is exactly what CDM would predict for a local universe, called a constrained realization. And this is what it would look like in neutrinos on the left. Well, on the right, you see what CDM predicts. I said that all these are familiar structures. And on the left is what the neutrino background would look like. It traces the same structures, but they're kind of puffed up. And here's in the pi diagrams of distance versus right ascension. This is what you would see in CDM, and that's what the neutrino background would look like. It traces the local large-scale structure, but it's kind of puffy because these particles are moving much faster than the cold dark matter. And so, and here is where these are galaxies. I think the red things here are the real galaxies, and you see then the neutrino background. And one exciting thing is that if you compute the angular power spectrum, just like you do for the CMB, then the predictions are very different depending on the neutrino mass. So if the background is ever discovered and we don't know the measure, we don't know what the neutrino mass is, you can just read it off this plot. And that's for masses ranging from 0.05 eV to 0.15 eV. And there's a whole range of rich neutrino science behind this. But I just wanted to tell you about that. And let me come back to the main theme, which is how do you rule out CDN? Right. So we go back to this plot. And so you might say, well, I show you this picture before of the cold and warm. Let's count things in the universe. Now, unfortunately, you can only count easily things that you can see. And the problem is most of these halos you cannot see. Most of these halos are completely dark, and only a tiny number of them light up. So I'm going to give you a one-slide tutorial on galaxy formation. So those of you who don't work on galaxy formation, this is the essence of galaxy formation. So it occurs in two phases. Just after recombination, the hydrogen is neutral. That's phase one. Now, neutral hydrogen doesn't cool. It can only cool if it gets ionized, and for that it needs to fall into a halo, and the halo has to be above some mass. So before reionization, just after in the dark ages, galaxies can only form in halos above a threshold mass. And I'm going to tell you what that mass is in a minute, because in smaller halos, the gas just does not collapse and is able to cool. So halos smaller than this critical mass never make a galaxy simply because the hydrogen cannot cool. Then the universe gets reionized, and we enter into, so the first galaxies that form here produce UV photons, they reionize the universe, and then they heat up the gas as well. And so there's a second phase after recombination, after reionization, where the gas gets heated to 10,000 Kelvin, and then you have another threshold slightly higher than the first threshold. Right? So there are two thresholds. Before reionization, the mass has to be bigger than something. After reionization, has to be bigger, the halo mass bigger than something slightly bigger, because the gas is now at 10 to the 4 Kelvin. The result of this, and if you want to see the details, they're in a paper. You can't see it there, unfortunately, but by my former postdoc, Alejandro Benitez Lambay, and myself, we published this in 2020. And this is one of my favorite plots in galaxy formation. And in this context, what's plotted here is the fraction of halos that managed to make a galaxy as a function of the mass today, not when they were making the galaxy today. And you can see here that all halos of mass less than about 3 times 10 to the 8 are dark, 100%. There's zero galaxies in these halos. And then above 3 times 10 to the 9, 100% of them have a galaxy. And there's this very sharp transition between them. So halos less than 3 times 10 to the 8 are completely dark. And the physics, thanks, Paulo. The physics are absolutely trivially simple. It's just hydrogen cooling. That's it. There's no magic. There's no supernova. There's no nothing. It's just hydrogen cooling. Then above 3 times 10 to the 9, they all make a galaxy. Now, most of the halos, you saw that power law mass function, are, of course, of mass less than 3 times 10 to the 8. So a tiny fraction of halos make a galaxy, and only that small number are visible. And this was known for a long time. It was known before it became a problem. So many of you would have heard about the missing satellites problem, which makes me go apoplectic because the problem was solved before it became a problem. This is a plot from 2002 from my student then, Andrew Benson, from his thesis. He computed the luminosity function of satellites of the Milky Way. And here are his predictions, just using the simple physics. Well, there was a bit more here, he had supernovae and so on, but that's just the icing on the cake. The physics is very simple. And here are the predictions, lots of scatter here at the large mass end. And here are the data then. Actually, when Andrew wrote his paper in 2002, only 11 satellites were known. We now know more, about 50 or so, and the agreement is just perfect. So there's never been a missing satellite problem. There's only been a missing galaxy formation physics if you talk about the missing satellite problem. So I hope, keep saying this. I've been saying this for decades now. I really don't want to go to a conference and hear people talking about the missing satellites. And if you still think there's a missing satellite, or it's too big to fail, or all this kind of stuff, and you're going to write a grant proposal, make sure you have a covering letter. Do not send this to Carlos Frenk to referee, because I won't even read it. Those problems do not exist. Go read the literature. And it's not just Benson. I mean, after Benson, there's been countless papers solving the missing satellite problems time and again. So, and it's just simple physics, right? So that counting satellite is going to get you nowhere. So how can we test CDM and distinguish it from warm dark matter? Well, these are, I said, all these are dark. So you have to be able to see in the dark. So instead of counting faint galaxies, what we need to do is count totally dark halos, starless dark halos. Now, how do you do that? Well, it turns out you can do that through gravitational lensing. And so now gravitational lensing with today's techniques would only allow us to see this part. But this is enough to, for example, distinguish CDM from warm dark matter, because that's what warm dark matter is. So if you, there's always a way out. Probably Alexei will tell you about a way out. But in any case, if you're able to find halos, dark halos of mass 10 to the 7, then you'll kill off the most interesting warm dark matter models. But more than that, we tell you exactly how many you should find. So if you don't find the right number, then you also rule out CDM. So there's no ambiguity. And this is a beautiful test because baryons are not involved. I mean, they're involved here, of course, but we just agreed that that's not interesting. In here, there are no baryons. These are dark things. And they may interact with baryons if they go through the disk of the Milky Way and things like that. But for the most part, these are objects that have never seen a baryon. And so and we know exactly from the simulations how many you should find. So if you find none, then we're in a warm dark matter world. And if we find too few, I don't know which world we're in. But if you find the right number, then you get begin to validate the idea of CDM. But that's a way to rule it out. Now, how does this work? Well, actually, we saw this plot the other day at a talk in lensing. So if you have a source of light and you have a big object, massive object, a lens, a galaxy cluster, and you have an observer, and if they happen to line up, as in this picture, then you get this amazing optics effect called the Einstein rings, which is some most spectacular phenomena that nature shows. So now, so that's known, but now we're not interested in that. What we're interested in these small objects of 10 to the 7 solar masses or 10 to the 8, but they don't produce Einstein rings, but they also produce gravitational lensing, and then they distort the Einstein rings. Here's an example by Simona Veghetti, who discovered one of these distortions. You can see it here 15 years ago, or 13 years ago. And now the thing is, you can see the object here that's causing the distortion. If you can see them, they're not interesting because they're very massive. So the one she found has a mass of 2.8 times 10 to the 10. So you can see the galaxy there. We're not after those. We need to do the same experiment with 1,000 times better resolution. Now, here's the way it works. This is for an example of a 10 to the 10 solar mass halo. So you take an image of a Einstein ring, then you fit the model of the source and the lens called the macro model, assuming that there's no substructure or there are no small halos on the line of sight. You subtract the two, smooth model from the data, and then you get residuals. And these residuals are a sign of the presence of a substructure. So in the case of a 10 to the 10 solar mass halo, well, they're obvious. You see them there. There's no ambiguity in the residuals. It's much harder. Oh, actually, I should say we found ourselves some recently, but also very big, not interesting. This is some papers by James Nightingale, who was part of my group on this. We even found one in JWST. We found another lens. This is my student, Sam Lang. Again, not that interesting, a very massive object. But my student, Chu Han He, who was mentioned the other day in a different context, he assures me that one can detect 10 to the 7 solar mass halos with these techniques. Here, the residuals for the 10 to the 7 solar mass halo, much harder to spot. But in principle, this technique should work. And so I think there is a hope we can detect halos as small as 10 to the 7 solar masses. And if warm dark matter is right, then we should find none. It should be a null experiment. So if warm dark matter is right, they're not 10 to the 7, they're not 10 to the 8, we shouldn't see anything. Of course, we have to convince the world that we're not blind, that we cannot detect them. But if CDM is correct, then we should see lots of these 10 to the 7 solar mass halo. And as I say, we know how many we should see. Right, so that's this test. We still have lots of mass function here to go. So how can we see those? Well, it turns out we can see these too, but a completely different technique, which is annihilation radiation. So this we heard a lot yesterday and the other day about annihilation radiation. If the dark matter is made of Majorana particles, they have their own antiparticle, and so when they come together in dense regions like the center of the Milky Way, they annihilate. And if the mass is in the GeV range, they produce gamma rays. And we saw this formula the other day, the intensity of radiation depends on an integral along the line of sight of the square of the density, because it's a two-body effect. It's annihilation, you need two of them. And so it goes like the square. And the main thing is this particle physics. We know all that. And this is, I just told you what the density profiles of these things are. They're NFWs with a twist that I'm about to tell you in a minute. So, right. Now, here's the twist. This is a plot from, I stole from you cannot see the attribution is from Sven Delos and Simon White this year. Now, so the plot here is the density as a function of radius in parsecs, right? So you see here, let's look at the green, sorry, at the red at redshift 73. This is a very early time for a halo at redshift. Actually, 37 is the green. And it looks like NFW, perfect NFW, until you get to 1/10 of a parsec. So this is a very, very central part of this Earth. This is an Earth mass halo, the ones I was telling you about before from the VVB project. So if you look at 1/10 of a parsec right in the middle, then there's this phenomenon that they call prompt cusps, where the density is actually steeper than NFW. It's only in the very center and only for the halos near the cutoff, right? But most of the halos are near the cutoff. The mass function is goes like 1/mass. So all the halos, most of the halos are near the cutoff, the Earth mass. And right in the center, there's a very steep cusp. But because the annihilation radiation goes like the square, these dominate the gamma ray annihilation. Now, that is a complete change of paradigm. Now, however, near the center of the Milky Way, there's another paper by Delos and White. They call them prompt cusps, because as soon as these Earth mass halos collapse, then this cusp forms very promptly. Now, towards the galactic center, these prompt cusps get destroyed by tidal interactions with stars. So near the galactic center, there are no prompt cusps, and the situation is as we knew it before. But outside from the galactic center, then these prompt cusps dominate the gamma ray annihilation radiation. And the extragalactic sky is mostly, the gamma ray background should mostly be coming from these prompt cusps. And now because the emission now comes from individual blobs, then it scales like the number of blobs, no longer like the square of the density. So here is a plot that shows the galactic center excess. I'm sure most people here realize that Fermi, actually data from Fermi, but it was really Dan Hooper, discovered a gamma ray glow near the center of the Milky Way, which has all the appearance of dark matter annihilation. It's extended, it has an NFW profile. That one remains as before because the prompt cusps get destroyed there. But if you move away from the center, then the prediction is that the flux of gamma rays should be more or less constant as you move away from the center from 20 degrees onwards. And if you look outside the Milky Way, there's a background produced by prompt cusps, and that background you can compare with the measured background, and it's just marginal at the moment. So there's a slight tension between the observations of the gamma ray background and the predictions of the prompt cusps, but it's only very mild. And if you're pessimistic, you call it a tension. If you're optimistic, like I am, you call it a detection. We've seen prompt cusps. We've seen the gamma ray background is produced by these Earth mass objects, and job done. So Dan Hooper can book his ticket to Stockholm. So I think I'm done. And yeah, I am done. So what have I told you today? The properties of CDM in the absence of baryons. I could give you an entire new talk, but I won't, Pablo won't let me, on what happens when you have baryons, but that is a solved problem. The abundance and structure of CDM halos down to the Earth mass and warm dark matter halos, which don't exist below 10 to the 8 for interesting warm dark matter candidates, is now known. CDM and warm dark matter, I didn't show you this, but it's true, of all masses have NFW density profiles, except in the very inner parts for halos near the cutoff, which have these prompt cusps. So this is just what CDM predicts, Paulo. I'm not saying the universe is made of CDM, but this is what CDM predicts. There's no small-scale crisis of CDM. I didn't tell you too much about that, but I did tell you about the neutrino as a digression, the cosmic neutrino background, which would be very interesting if it could be detected and will allow us directly to measure the neutrino mass. Although we may measure the neutrino mass before from plots like the one I show you from DESI. And finally, almost distortions of strong gravitational lenses, lenses offer a very clean test of CDM and warm dark matter, can potentially rule out CDM. And then the annihilation radiation is again a very subject where many things are happening, and both in the theory and in the observations. And it'll be very interesting to see what the next generation of gamma ray telescopes, particularly CTA, we heard a talk about that the other day, what they have to tell us. And I will stop here.